Okay, so chapter 1, bonding and isomerism. We need to review some general chemistry. There's a reason they made you take general chemistry before you could take this class. So thinking about atoms and how the electrons are arranged in the atoms. Atoms have an internal structure. There are 3 subatomic particles that are present in almost all atoms. There's a whole bunch of other little tiny ones, but these are the only ones we care about. There's a proton. Proton has positive charge. It is very tiny. It's 10 to the minus 27 kilograms, but it is much larger than an electron. An electron is 10 to the minus 31 kilograms, almost 2,000 times smaller. So the proton has significant mass on an atomic scale, and the neutron also has significant mass. The mass of the neutron is almost exactly the same as the proton, but the proton is positive. Proton starts with a P, positive starts with a P. A neutron is neutral, and the electron has a negative charge and is much smaller. So most of the mass is concentrated in the nucleus of the atom. So here's an illustration of a nucleus. That's the protons and the neutrons. Those are all in the nucleus, and then the electrons are on the outside somewhere. So we'll talk sometimes about atomic number. Atomic number is the number of protons that an atom has. And that we can figure out from the periodic table. If we look at in this periodic table, the number's in red. So for carbon, it's in a box with a red 6. The whole number is the atomic number, the number of protons that element has. And the atomic number is what identifies an atom as belonging to a particular element. All carbon atoms have 6 protons, every single stinking one of them. The atomic weight is approximately equal to the number of protons and neutrons in the nucleus. So if you have 6 protons and 6 neutrons, the atomic weight would be about 12. And then the electrons. And the electrons we're very interested in because they affect how atoms interact with each other. So atoms will have 1 or more electrons, and the electrons are the negative charges, and they're going to be in constant motion somewhere outside the nucleus. And exactly where they are is kind of mysterious and hard to understand. The number of electrons, though, is always equal to the number of protons in an atom, because an atom does not have a charge. So the number of positive charges and negative charges has to be equal. So we've got those electrons running around. Here's an illustration that's kind of helpful to think about. These electrons just kind of zipping around. This is an easy way to think of it. It's not really an accurate description of what an atom is like. But we can see by looking at this picture, there's a lot of empty space. The nucleus is in the center, and most of the atom is empty space, and there's these little electrons. If the nucleus of an atom was the size of a green pea, and you put that on the 50-yard line of a football field, the neighboring atom, well, let's see, the atom would be about the size of the entire football field from end zone to end zone if the nucleus was the size of a pea on the 50-yard line. And what is in all of that space? A few electrons that are much, much smaller than the nucleus. And so the atom is mostly empty space. There are different ways of describing, or there's different theories about the location of the electrons and what they're doing. Quantum mechanical theory is the current theory in use and our best understanding of how electrons are arranged. So quantum mechanics teaches us that electrons are concentrated in regions of space around the nucleus called orbitals. It's easy to think of atoms orbiting the nucleus, like in this picture of, that this electron is orbiting the nucleus, but that's not what they're doing. They're actually in orbitals, which are different. It's actually a region of probability in which you have a likelihood of finding electrons. These orbitals have different shapes, and they're designated with letters, S, P, D, and F. And this should be review. Each orbital can hold at most 2 electrons. Sometimes they have no electrons in them, sometimes only 1. And those orbitals are grouped into shells, which are indicated with numbers, 1, 2, 3, 4, etc. Each shell is going to have different types and numbers of orbitals depending on the shell number. So we're kind of given the baby version of quantum mechanics here. So in shell number 1, there's 1 s orbital. In shell number 2, there's 1 s orbital and 3 p orbitals. In shell number 3, we have 1 s orbital, 3 p orbitals, and 5 d orbitals. And since each orbital can hold a maximum of 2 electrons, we get the number of electrons that can be found in that shell, maximum of 2 in the first shell, 8 in the second, and 18 in the third. Any questions? Do you remember hearing about this stuff?
So when looking at the periodic table, like hydrogen would be 1s1, and then the helium would be 1s2?
Yes. Yep. Yeah, it's all pretty much laid out in the periodic table. We can just look at it and predict, like silicon would be 1s2, 2s2, 2p6, 3s2, 2p2. And we'll look at that sort of a configuration in a minute. What we're most interested in are the valence electrons. The valence electrons are the ones in the highest occupied shell. So those shells are like broad categories, and as the number increases, the energy increases and the distance from the nucleus increases. The valence electrons are the one in the outermost shell. And these are Lewis electrons dot structures. They go by many names. Lewis dot structures for some of the elements. The element symbol, like H for hydrogen, is going to represent the kernel, which your book calls the, I've not used the term kernel before, but whatever. That would be the nucleus and any inner electrons. Now, hydrogen doesn't have inner electrons. But if we look at sodium, sodium has 1 electron in the highest level, and the rest of its electrons are all on the inside. And so when we show these diagrams, we're using the element symbol to represent the nucleus and all of the core electrons, and we use the dots to show just the valence electrons, the one in that highest shell. The number of valence electrons that an atom has corresponds to the group number on the periodic table. Periodic tables tend to have 2 different kinds of group numbers. The IUPAC one that's used worldwide, and then the current US usage, which would be the 1A, 2A, 3A, usually with the Roman numerals. I figure since we're currently in the US, we can use the current US usage. I find that it gives us a lot more information. But if we look at hydrogen and lithium and sodium, they're all in group 1A, and they each have 1 valence electron. If we come over here to group 7A, fluorine has 7 valence electrons, chlorine has 7 valence electrons. All of the noble gases have a full shell of valence electrons. Helium has 2. It's the 1s2 orbital, it's full, and there isn't room for any more. Helium has 8 valence electrons, and argon has 8 valence electrons. Remember this stuff? We're coming back? We got to go over it because, you know, it's been at least a couple months probably since you had this class, and so you get a little rusty. Here's some other important principles that may or may not have been emphasized in your previous chemistry class. Pauli exclusion principle tells us that no 2 electrons can have identical quantum numbers. And the important takeaway from this is each atomic orbital can have at most 2 electrons. You just can't have more than 2. The Aufbau principle tells us that the atomic orbitals are filled from lowest energy to highest. When we say that an orbital is degenerate, it means that it has the same well, you can't have just one degenerate orbital, you have to have more than one. Orbitals that are degenerate have the same energy. So there are 3 different 2p orbitals, and there's the px, the py, and the pz. And it's just their orientation in space. They all have the same energy, so we say they're degenerate. And Hund's rule tells us that the electrons will occupy those orbitals individually with parallel spins before they pair up. So another way to say that is the electron configuration with the highest multiplicity is more stable. That probably doesn't make a lot of sense. So let's look at this here. Now I'm going to draw on this. If I had been able to create this, I would have done it without all the little red arrows on there because I'm going to draw them in myself. So this shows us the order of these orbitals. So here's the first shell with its 1s orbital. Here's the second shell. It's got 1s orbital and 3p orbitals. Those 3p orbitals are degenerate. The third shell has 1s. My iPad was very dirty before because my 5-year-old Andrew was playing with it, and now I made it too clean, and my stylus is squeaking, and it's just driving me bananas. Just have to deal with it. There's 3 p orbitals and 5 d orbitals, and they will fill in this order. So if we have 1 electron, it'll go in here. The second electron will go in here because that is the lowest energy. Energy is a little bit like money, and these electrons are tight with their money. They're going to go for the lowest energy, the cheapest place to be. And so when that one's full, the next electron has to go up here, and the 4th electron would go in here. The next electron will come up here. Now, this is a little bit like taking seats on a bus. Have you guys ridden public transportation? So you get on the bus, and there's like 4 completely empty seats, and all the other seats have 1 person in them, and you don't know anyone on the bus. Do you sit with a stranger, or do you take your own seat?
Empty seat.
You take your own seat, right? Why would you sit with a stranger? Unless she's like really hot or something, but we're not going to go there. So the electrons do the same thing. The next electron comes in, he's like, I don't want to share with that guy, I'm going to take my own seat. Same energy, why not have an orbital to myself, right? So he's going to go in here, and the next one's going to go in there. Once all the seats on the bus are full of one, not full, but half fill, have 1 person, you get on the bus, then you're going to have to sit by somebody, right? So then the next electron comes in here, and the next one in here, and they'll fill that one up completely before they go on up to the next level. Now, if we were stopping here, how many electrons have I put in there? 11? I think 11. So 11 electrons is which element? I know it's tiny. It's sodium. So this element, having 11 electrons, must have 11 protons because the number of protons and the number of electrons is equal, and so this is sodium. So what we have here is this order of filling type diagram, but we often abbreviate that and do what's called an electron configuration. So there's the 1s orbital, and that's got 2 electrons in it. And then the 2s has 2 electrons. And the 2p orbital has how many? 6. And the 3s has how many? 1. Okay, so that would be an electron configuration for sodium. If we look at carbon, carbon has an atomic number of 6. So if we were to fill in, this is what we would end up with. Now, we need to be able to identify a number of valence electrons. Valence electrons are the ones in the highest shell. So here we have 2 shells represented, shell 1 and shell 2. How many electrons are in shell 2? 4. Okay, it's not just this level up here, it's all four of these guys. So those are the valence electrons. Let's look at oxygen. Which are the valence electrons? How many are there? There's 6. It's these in the second shell. Okay, when you get up to the third shell, it's just however many are in the third shell. Any questions? So chemical bonds that's a term for the forces holding atoms together. We're going to talk about ionic bonds and covalent bonds. Valence electrons, we just mentioned, electrons in the outer shell. Lewis dot representations or Lewis dot structures. We show dots around the chemical symbol of an atom to represent the valence electrons. So I think we're doing pretty well. We'll just do one of these. Let's do boron. Boron's fun because it sounds like moron. Give the orbital filling diagram, the electron configuration, and the Lewis dot structure for boron. So first thing we have to do is find boron on the periodic table and figure out how many electrons does it have. 5, right? So 5 electrons. So then if we're going to do that orbital filling diagram, we have 1s, and we've got 2s, and then next is 2p, and we're probably going to be okay with that. And then we'll take those electrons and we'll put them in. There's 1, 2, 3, 4, 5. So we're just putting them in, lowest energy to highest energy, and then that would be the filling diagram. The electron configuration, we're just going to kind of summarize that. It's like a chemist's shorthand. 1s, 2, 2s, 2, 2p, 1. And as a check, you can always add up these superscripts. They should add up to the same number of electrons that that atom has. How many valence electrons does boron have? 3. So then the Lewis structure for boron will be the element symbol, and then we'll have dots. I think my dots are going to be too big. It has 3 dots, so 1, 2, 3. When we write those dots, we use the positions top and bottom, right and left, and just sort of as a convention, just like filling the seats on the bus or the orbitals, we're going to put them in singly and then pair them up. So this is a good Lewis structure for boron. This is not the best, pairing those up. Okay? Any questions?
How did we figure out that it has 3 valence electrons?
How did we figure out that it has 3 valence electrons? That's very good. Well, we can look at this orbital filling diagram and we see that the highest level is 2. And there's 2p and 2s. Those are both in the second shell. And so how many electrons are in the second shell? There's 3.
Okay.
If we look at the electron configuration, here's 2. That has 2 electrons. And this is also 2 and 1. So 1 plus 2 is 3. We can also look at the periodic table, which I think I'm going to get to in a minute. But the group number tells us the number of valence electrons. Oh, yay, there's the periodic table. This is my favorite periodic table. I actually have a favorite periodic table. So there's the IUPAC notation. I prefer to ignore those. And here's current U.S. usage. Currently in the U.S., let's use it. Right? That one has IUPAC on it. If you have a periodic table that only has the IUPAC numbers, just ignore the 1s in front of them. So this is group 3A or 13. So just look at the 3. Here's boron in group 3A. It has 3 valence electrons. Here's nitrogen in group 5A, 5 valence electrons. Okay. It's really important to be able to identify how many valence electrons an atom has.